Hi everyone. This lesson that we're going to be taking a look at is something that we looked at in class. This is projectile motion. Now the title says uniform acceleration and projectile motion. I'll try to mostly deal with projectile motion. I might talk about uniform acceleration for a couple of minutes in there. Okay. Alright, so these are some questions. These are just uniform acceleration questions. It might be a good idea that you try them at home for practice. Okay, again, these are questions dealing with acceleration due to gravity. Okay, when it comes to projectile motion, as we talked about in class today, projectile motion, there are a few rules that we need to make sure we are going to take a look at, and one of them is as follows. Okay, the first thing we said when we're looking at projectile motion, we said objects that don't fly of their own fruition. Okay, so they're not flying because they have the ability to fly, rather they are moving through the atmosphere. Number one, close to the Earth's surface. Number two, of course, we also said these are objects on which there is only one force, and that is being the force of gravity. As another assumption is that friction is negligible. All right. Another thing that we talked about here, force of gravity, friction is negligible. So because friction is negligible, the only acceleration that we have is acceleration due to gravity, and that is in the y direction. Now we also said that since there is no other force that is acting on it, in the x direction, the velocity does not change. It stays constant since there is no net force. If there is no net force, then therefore there is no acceleration. If there is no acceleration, your velocity stays constant. Okay. Another thing to remember with vector components, as well as in projectile motion, is that our uniform acceleration formulas that we've been using, now we're going to divide these formulas into their x and y components. So for the x direction, as we said, there's only one formula that we're going to take a look at, which is Vix, okay, times t. Vix times t. This is the only formula it needs, which is pretty much v equals to d over t. That's pretty much what it is. In the y direction, we have a couple of different formulas. So now you're used to the formula delta d equals to vit plus half a t squared. So we're going to change that to delta y, which equals to viyt plus half a t squared. Okay. Another one that we could use, delta y, which equals to vfyt minus half a t squared. And of course you could also use vfy squared, which equals to viy squared plus 2a delta y. Now these are some of the formulas that we may use. Of course you can also use a y equals to vfy minus viy divided by t. You can also use this. These are all some formulas that you can use in the y direction, and this right here in the x direction. Okay. Now a few things of note before we go any further, which is that when we're looking at any projectile motion question, now the projectile will make the shape of a parabola as it is flying through the air. And as it's flying through the air, as we said, the x component of velocity is not changing, and we notice that right here. Vx not changing, staying the same all the way through. The y component, however, is maximum at the bottom. As you could see, maximum starts to decrease, and at maximum height, this being your maximum height, your y component goes to 0. And we've talked about this. If I was to throw a ball into the air, the ball would slow down its speed. when it gets to the top of its motion, it would literally stop for a fraction of a second and then continue downward. And this is what we're looking at when we're also looking at projectile motion as well. Now this horizontal line, which will give us the range of how far my object fell, how far away from the origin did this object fall down, and that would be your delta x. Your max height is known as your delta y. Now your the Vy component, my bad here, the Vy component, as it's decreasing, as it goes to 0 and continues to increase as it comes down, if your object is starting from the ground, ending up on the ground, then your Viy component and your Vfy component will be the same, except the Vfy will be in the opposite direction. These are just some things that we need to remember. Now we talked about 4 cases that we're going to take a look at. So we can start from ground to ground. Okay. Ground to ground. This is your most obvious one. You'll give your delta x here. That will be your maximum height. You start at a certain time t equals to 0, and you end up at a certain time, whatever that is. Okay. Second part of the second situation that you could have is that you start at a maximum height. So you start at delta y being max height, and you drop downward towards the ground. Case number 3 is where you might start at any other height and you end up lower than before. You end up lower than before. So you have a delta y to already begin with. This would still be your maximum height, max height. Okay, and that would still be right here your range. Of course, situation number 4 is the opposite of this, where you start on the ground and you end up on another height. Okay, and here this delta y there would be the height that you've gained, and this would be your maximum height. So these are the 4 situations that usually, these are the problems that you usually get when we do projectile motion questions. Okay, now look, when we're looking at the acceleration due to gravity, just a few things to remember. That acceleration is always caused by a net force on an object. Now when that object is falling through the air towards the ground, that net force, of course, now becomes the force of gravity, Fg. Okay. Now we have learned in class that an object, as it's falling towards the ground, the acceleration of that object does not change no matter how large that mass is. So mass does not affect the acceleration of the object as it is going towards the ground. And close to the Earth's surface, and that's being very important, close to the Earth's surface, the average across Earth is 9.8 meters per second squared down towards the center of the Earth. Now, of course, this is not the same all throughout Earth. There are some parts of Earth where this force might be a little larger, and some parts where it's a little less. Why and how do we know that? Well, we know that the equator is, the radius of the equator is a little larger from the center. So here, the Fg is a little less. Okay, slightly. We're not talking about very large. And at the poles, my radius is a little smaller, slightly smaller, so my Fg is a little large. Slightly larger. Okay. All right. Just make sure you read through this. We talked about examples from before, where whether it's a grape or a grapefruit or an asteroid, if there was no other force that is acting on it, if there was no air friction, then they would all be falling down at the same rate. Okay. All right. So projectile motion. Now this is an example of projectile motion. Take a look at it. This is an example of case number 4. Case 4. Okay. The object is starting at a ground lower than where it ends up. It ends up higher than where it started. Okay. Now in this situation, the question says, what is the time interval, what is the horizontal distance, and the velocity of the ball just before it hit the ground. So before we start, we're given our VI. Break it down into its x and y components. So VIX, VIY. This is the most basic step. At least do this before we start anything. That way you are on your way. You can get questions done. Your VIX, of course, is going to give us cos of 65 times 32.6. Make sure you calculate that on your own. Okay, VIY component would be sine of 65 times 32.6 meters per second, and you'll get a VIY component. Okay, once you get this, then we can continue to figure out our time, and to use our time we might use delta y, which equals to VIYT plus half AT squared. Now a few things of note that we need to remember when we are looking at these problems. Look at velocity and acceleration. If my velocity, as we see in this situation, my velocity is going upward, okay, I'm going to make this velocity positive. Since gravity is against this, so here gravity is going to be negative. So this is something to remember. Okay, so velocity going upward, velocity is positive. Gravity is going downward, gravity is negative. So in this situation, your delta y will be positive right here, and that gives me a number of 6.30, which equals to whatever VIY that you get from here times t. Now the half, and because acceleration due to gravity is negative, so that'll be half times negative 9.8, which will give you negative 4.9. So that'll be minus 4.9 t squared. Of course, here we'll have VIY. Of course, we'll have to use the quadratic equation, negative b plus minus b squared minus 4ac divided by 2a. Okay, figure out t1, figure out t2. Now one of them will be negative, one of them might be positive, or both of them might be positive. It depends on the situation. And as soon as we have figured out our time, we take the proper time, then we can continue to figure out what our horizontal distance is. Now to figure out our horizontal distance, we just use delta x, which equals to VIX times t. Now that would be that VIX that we see from this situation right here, and we would just put that in and figure out one of the times, put that time in, and we get delta x. So hopefully this is something that will help you. Please make sure you do go through these questions. Try to do it on your own, and please make sure you can ask in the class if you have any problems. We do have drop-in center Tuesdays and Thursdays, 3 to 4:30. So you may also come there and ask me. All right, this is an example of a situation, case number 3, where we're starting at a higher spot and going lower. Now the problem has been solved right here for us on this page, and it's been solved slightly differently than what you might see. You might see some slightly different variables. Regardless, they all mean the same. So as we said, we would start with VIX, which is given to you, which has been solved for us right here. Okay, that's actually VIY. Okay, so VIX is 26.8 meters per second. There is your VIX. There is your VIY. VIY would be 22.5 seconds, meters per second. Okay, figure out the time. In this situation, since I'm starting at a height larger or above ground and literally losing height, my delta y is negative, so it will be negative delta y. Okay, delta y, which equals to VIYT plus half AT squared. Okay, so delta y is negative, so negative 20 meters, which equals to 22.5 times t minus 4.9 t squared. As we said again, velocity is upward, okay, acceleration is downward, so therefore negative. Now use your quadratic equation. As you could see from here, quadratic equation, you figure out the time. There is your negative time, which we are going to disregard, and there is our relevant answer, which gives us our time, and this gives us our x direction, the dx, which is how far this ball traveled to get at the end. Hopefully this has helped. Again, as I said, please make sure to ask questions in class. Thank you very much. Have a good night. Bye.